One of the things that you may notice throughout our study of organic chemistry is that there are relatively few reactions that form new carbon-carbon bonds. Carbon-carbon bonds are one of our more stable bonds, and so they tend to be somewhat difficult to break and form. We're usually reacting at our bonds between carbons and oxygens or carbons and our halogens, right? Because those bonds are very polar and much easier to break compared to our carbon-carbon bonds. Now in our last video we looked at these conjugated dienes that could react in new ways because of those two alkenes working together. And it turns out we can actually use those two alkenes working together in our conjugated system to make new carbon-carbon bonds as well. Specifically, we're going to be able to make ring systems using this Diels-Alder reaction. Our Diels-Alder reaction occurs between a conjugated diene and an alkene. This alkene we refer to as a dienophile, because of course it's going to be reacting with and joining with our diene. So our reaction here is very interesting. So it occurs in a concerted mechanism, right, which means that everything is happening together, and it involves a cyclic movement of electrons. So we're going to take our extra electrons from our double bonds, and we're going to attack one of the carbons of our alkene. Now, of course, if we just attack this carbon already has our two hydrogens here, so it has its full octet, and we can't add a new bond there unless we also take a bond away. So we're going to take the electrons from this double bond, and we're going to attack the other side of our diene. Now again, of course, as we're attacking and bringing those new electrons in, we also need to move our double bond out of the way to make room for those new electrons. So if we shift this over here, we can replace the electrons that our carbon here lost as we attacked our dienophile. So the end product here, after we move all those electrons around, so we have our diene here. We lost this double bond, but made a new bond over here to our alkene. We used our double bond to make a new bond up here to our diene, and our last double bond just shifted over to take the place of our lower double bond that we used to make that new bond. So we have a cycloalkene as our product, and this all occurs in a single step through our electrons moving around in this cyclic reaction. Now, as you look at our reactions, you might wonder, our alkene right here, right, we tend to say alkenes are almost somewhat nucleophilic because of the extra electron density of that double bond. So why would our diene want to attack this alkene that's already happy with the electrons it has? Well, the truth is that this reaction would be somewhat slow because there isn't really a strong incentive to attack that alkene. The best incentive really right now is just that we form this relatively stable 6-carbon ring system. So if we want to speed up our reaction and make it more likely to occur, what we can do is add electron withdrawing groups onto our dienophile or our alkene here. So an electron withdrawing group would be any kind of electronegative group that might help to pull electron density away from that alkene. Right, so if we add our double bonded oxygen up here, what we call a carbonyl, so that's of course going to be pulling electron density towards itself, towards that electronegative oxygen, and of course that electron density also affects the rest of our molecule through an inductive effect. So any kind of electronegative groups that we can add on here off of our alkene will help to pull electron density away and increase the rate of our reaction. So we can say that electronegative groups increase the rate. So that will pull electrons away, so that encourages our diene to attack. We would again have our cyclic movement of electrons. Of course, in this case then, we would still have our carbonyl up here attached to our product. Right? Remember, all of this stuff over here is our dienophile. And all of this stuff over here is from our diene. Okay, so we have those two things combining together to make our final cyclic product. Now the structure of our diene will also affect this reaction as well. Now the first thing you should notice is that our two alkene bonds of our diene are both pointing in the same direction. So you could say they're cis relative to each other. Now of course this isn't a true cis diastereomer because of course this central bond can freely rotate. Right? So we could rotate it and have our same diene like this just by rotating our single bond here. So it's not truly a cis conformation, but instead we say it's S-cis. Right? So it's not a different diastereomer, it's just a different conformation. That would be S-cis, this would be S-trans. We can rotate that bond around. We have to point them in the same direction for our reaction, or we can point them in opposite directions in this S-trans conformation. Now, of course, normally we can easily rotate back and forth between either of these conformations. But let's say we add a bunch of carbons out here in our S-trans conformation. Well, now as we go to rotate this bond, right, so we rotate around here to get to our S-cis conformation. So we have our alkene double bonds pointing in the same direction. But now we have these really large T-butyl groups both pointing in the same direction. And we get a lot of crowding between these two groups. So that crowding would actually make our S-cis conformation less stable, which would make our diene want to stay in our S-trans conformation and make it less likely to react in our Diels-Alder reaction. So if we crowd that S-cis conformation, we can slow down our reaction. Another way that the structure of our diene can affect our reaction is, of course, if we have groups attached on the other side of our double bonds. Right? So if we add some carbons over here, our alkene, of course, has to come in and react with our diene, and any kind of carbons or other groups on here will kind of add to our crowding and slow down that reaction. Right? So we're still trying to add on with our cyclic movement of electrons. It's just that now these extra carbons up here will crowd our reaction and slow it down. So any kind of crowding, whether it's just making our S-cis conformation less stable, or whether it's sticking in here and getting in the way of our Diels-Alder reaction, will slow down our reaction. So adding electronegative groups increase our rate, adding crowding will slow down our rate. Now, as we look at these more complicated Diels-Alder reactions, we're also going to see a more complicated mixture of products forming as well. Now, one of the things you might notice is when we have these larger reactants that are coming together, we're actually going to have multiple possibilities for different stereoisomers in our final products. So here, of course, we're starting with different diastereomers. We have the trans diastereomer for our dienophile. For our diene, both of these double bonds are the trans diastereomers as well. So our product, of course, is a ring system where we can also have cis-trans diastereomers, or even R and S enantiomers, depending on the configuration of each of these different groups on our ring. So we need some guidelines to know what kind of stereoisomers we're going to produce from this Diels-Alder reaction. First, let's look at our dienophile. So in our dienophile, if we start out trans, then we're going to end up trans in our product. So if we draw our dienophile groups, trans, of course, on a ring would mean that one group will be pointing up, and the other group will be pointing down. So we have those two groups, one on a wedge, one on a dash, and then, of course, we have our other groups over here from our diene. We can sum up this rule by saying that the trans-cis configuration of our dienophile is retained. So that means if it starts trans, like in our scenario here, it ends up trans here on our cyclic product. Now for our diene, we of course could talk about our individual double bonds as being cis or trans, but actually what's more important here is to look at what groups are pointing out in our S-cis conformation and what groups are pointing in. So our two hydrogens are coming in. These are the things that would be crowding our reaction and potentially slowing it down if we had bigger groups here. And we have our two groups pointing out. In this case, our two methyl groups are pointing out. Those have less effect on the crowding of our reaction. And the rule here is that our out groups and our in groups will always point in the same direction. And that again, of course, is with respect to our ring. So we had both of our out groups will then be both sharing the same direction in our product. Right, so they could be both on wedges. So they started out pointing out, and they both start pointing up in our product, which would then, of course, put our in groups, our hydrogens, pointing down. Now we do have two different possibilities here. Right, they could both be pointing up, or they could both be pointing down. In this case, those would both be equivalent just based on the symmetry of our structure here. So here we have the two different possibilities from our particular starting reactants. So we have one possibility with our in groups pointing up, and one possibility with our in groups pointing down. And of course, for our dienophile, it's always going to be trans, regardless of what our diene is doing. Consider another possible scenario where both of our groups on our dienophile are cis relative to each other. So we have our cis diastereomer. Again, following our first rule, if we start cis, we're going to end up cis in our product. So they're both going to be pointing in the same direction. Now, of course, we already said that our out groups are both pointing in the same direction, and our in groups are both pointing in the same direction. So we have two different possibilities. We can have our out groups and our dienophile groups both pointing up, or we could have our in groups pointing up and our dienophile groups also pointing in that same direction. So I'm going to show this. So I'm going to draw our diene groups pointing in the same direction each time. So I'm going to have the out groups pointing up and in groups pointing down. And then from there, I could have my dienophile groups going up with my out groups, or going down with my in groups. So here they're going up. And over here, they'd be going down. So here's our two different possibilities then for our Diels-Alder reaction in this particular scenario. Now, in this scenario, right, we can refer to our dienophile groups as being cis to our hydrogens here, or we can refer to them being cis to our methyl groups over here. Right? Cis and trans aren't necessarily as useful here because we could refer to it as cis to in or cis to out in either scenario. Right? So instead we're going to use two new terms here. These terms are going to be endo and exo. So the term endo refers to when we are cis to the out groups, and the term exo refers to when we are trans to the out groups. So in this case we have two different possibilities. just based on the possible configurations of our dienophile with respect to our diene. And our third general rule then is that endo is going to be preferred over exo. So with these three different rules, we can generally categorize the different possibilities of our stereoisomers for our Diels-Alder reactions. Of course, as the complexity of our groups attached to our diene and our dienophile increases, we'll have more different possibilities for the number of different stereoisomers that we can produce, but we'll be following these same general rules for all of those. So far, we've seen a variety of different Diels-Alder reactions just based on changing the structure of our diene or changing the structure of our dienophile. Now, as it turns out, we can also do an intramolecular Diels-Alder reaction. So in this case, we just have a diene that's actually linked to our dienophile. Right? So we might have some carbons here connecting our dienophile alkene over here to our diene. And now at this point, we can do our same Diels-Alder reaction. Do that nice little cyclic movement of our electrons. So we have now our six-membered ring that we create in our reaction with our alkene over here on the left. And we would still have these carbons down here connecting from what was originally our dienophile and what was originally our diene. So this reaction can create some new cyclic systems within an existing molecule. Note, of course, in this case, we are producing two rings at once, since we have this loop here that's now connected by our new bond. So this reaction would only occur if we're forming a stable, generally 5 or 6 membered ring here. So we must form a stable ring. Of course, our ring that we form in the Diels-Alder reaction is always a 6-membered ring. Right, so we always get that one 6-membered ring. But then when we have our intramolecular reaction, often we're creating an additional ring as we're linking those two groups together. Now, one other interesting thing about this intramolecular Diels-Alder reaction is that we actually don't need to activate our dienophile to the same extent that we do in a normal Diels-Alder reaction. Right? So normally we try to add electronegative groups on here to make this more electronegative, to encourage that attack. But in our intramolecular system, here our reaction is just more likely to occur because our groups are fixed in position next to each other. Right? So it's easy for our group just kind of move around and find that other reactive unit, and so it makes this reaction faster compared to just a dienophile looking to find that random diene that's sitting in the same solution. Right? So just fixing those molecules close together means that our reaction rate is sped up, and this reaction is more likely to occur even though we haven't made our dienophile more electrophilic. Our Diels-Alder reactions all involve 3 different alkenes reacting. 2 are together in our diene, and then 1 is separate in our dienophile. Of course, in an intramolecular Diels-Alder reaction, we actually have a triene where they're all in the same molecule, but it's going to be 3 alkene double bonds reacting, regardless of whether it's intramolecular or intermolecular. Now, we can also actually get some similar looking rearrangements without that third double bond. So if we have 2 double bonds in this 1,5 arrangement, so this is a 1,5 diene, so we have our first double bond at the first carbon, and our second double bond here at the 5th carbon. Here we can use a cope rearrangement. So this kind of looks fairly similar to our Diels-Alder reaction, but it's not going to have that separate dienophile. So what we're going to do is we're going to bend this around to make a cyclic looking system. So we have our first, so we're just rotating here. We get our first alkene, 1, 2, 3, 4, 5, and our second alkene down here, and then our 6th carbon there. Now what we can do here with our 2 alkenes is we can do a cyclic movement of electrons similar to our Diels-Alder reaction. So we use our extra electrons to attack over here. This guy has to move out of the way. And now this carbon here is going to have too many electrons. So we actually take this single bond and break it to complete our cyclic movement of electrons and keep every carbon with a full octet. So after rearranging it, so we're going to have this bond breaking now. So we get our cyclic looking structure, but now we formed a new bond here with this arrow. We moved our double bond over here with that arrow, and our third arrow broke the single bond and formed a new double bond here. So we still have our diene at the 1st and the 5th position, but actually that methyl group, that single carbon, kind of shifted around. It was at the end, and now it's in the middle here because of this rearrangement of our electrons. Now this cope rearrangement is relatively rare because there really isn't a strong driving force to make it want to rearrange. So we do see it occasionally in structures where you might have a stability gain by rearranging it, but it's relatively rare. However, our Claisen rearrangement looks quite similar, but is much more common because it does have a strong driving force for this cyclic rearrangement of our electrons. So for our Claisen, we're going to have a very similar looking reactant. So we're going to have a 1,5 diene, but the difference here is we're going to add an oxygen next to one of our alkenes here. So we again have a 1,5 diene, but we have oxygen next to one of them. Again, we're going to fold it up into our little cyclic system. So we bend this around, so we've got our double bond here. We go over to our oxygen now, our second double bond, and that final carbon at the end. Again, we can do the same cyclic movement of electrons. And now in this case, so our structure is going to look very similar. We broke the bond over here between our oxygen and that carbon, but then we form a new bond over here between our 2 carbons. So we end up with our double bond here and our double bond up there, just like we did with our cope rearrangement. Now the unique thing here with our Claisen rearrangement, though, is that we produce this carbonyl carbon-oxygen double bond. So this is known as a carbonyl functional group. We'll talk about these more in organic chemistry too. And this carbon-oxygen bond is quite stable, and so that means that our Claisen rearrangement product is favored overall, right? Because we produce this stable carbon-oxygen double bond. So while our cope rearrangement is relatively rare, our Claisen rearrangement is actually quite common. As long as we have this diene with the oxygen next to our alkene, if we can rearrange it to make that carbonyl carbon-oxygen double bond, then we're always going to try to do that. So these Claisen rearrangements are something to watch out for. Again, just always be looking for that particular pattern of that 1,5 diene and our oxygen together so that they can rearrange to make our carbonyl. So our Diels-Alder reaction overall is somewhat unique in that we have this cyclic system getting created. You have this very interesting concerted cyclic movement of electrons in order to make that new product. As we see, we also have some interesting intramolecular rearrangements and reactions that can occur using a similar cyclic movement of electrons. All of these are quite important for systems where we have multiple alkenes within a molecule, or then multiple alkenes between molecules that we can use to fuse those molecules together. So they are quite useful overall in our organic synthesis reactions.